Welcome to MathMuni. Today we are going to tackle what seems like at first glance to be an impossible integral. It is not usual to encounter integrals that have the fractional part of x in the integrand. Usually, in such unprecedented cases, it helps to first start by building out a feel for the integrand by plotting it out. So we do that to begin with. Here's the plot of the integrand for x lying between 1 and 20. We see here that it has a sawtooth pattern with decreasing amplitude. It starts with a negative area between x is equal to 1 and x is equal to 1.5, then swings to the positive side between x is equal to 1.5 and 2, which partially cancels out the previous negative area. It then swings back to the negative side again between 2 and 2.5, which is then almost cancelled by the positive area from 2.5 to 3, and so on. These alternating area cancellations are never quite total, but as x tends to infinity, the area cancellations do become closer, and that is the reason why the integral from x is equal to 1 to infinity does not explode. And since the negative areas are always slightly bigger in magnitude than the positive ones, the final value of the integral ends up being slightly negative. That will be our expectation. Let's see how it pans out. Now let's get back to the integral itself. We start by recalling that n factorial is equal to n times n minus 1 times n minus 2 and so on till 3 times 2 times 1. Taking the natural log of both sides, we get ln of n factorial is equal to ln of n times n minus 1 times n minus 2 and so on till 3 times 2 times 1. Using properties of logarithms, this is equal to ln of n plus ln of n minus 1 plus ln of n minus 2 plus and so on plus ln of 3 plus ln of 2 plus ln of 1. Now the last term, ln of 1, is equal to 0. And the rest of it can be written in summarized form as summation ln of k, where k goes from 2 to n. Now note that the integral of 1 upon x dx between the limits 1 and k is equal to ln x, the limits of integration being 1 to k, and this is equal to ln k minus ln 1, which is equal to ln k. Using this result in the previous line, we can say that ln of n factorial is equal to summation k going from 2 to n integral 1 to k 1 upon x dx. Now the integral from 1 to k can be expressed as integral 1 to 2 plus integral 2 to 3 plus integral 3 to 4 plus and so on, and finally integral k minus 1 to k 1 upon x dx. This can be expressed as summation j going from 1 to k minus 1 integral j to j plus 1 1 upon x dx. Using this result, ln of n factorial is equal to summation k going from 2 to n, summation j going from 1 to k minus 1, integral j to j plus 1, 1 upon x dx. Now the summation on the inside, let's calculate its value for different values of k. When k is equal to 2, the expression on the inside can be written as summation j going from 1 to 1 integral j to j plus 1 1 upon x dx. And this is nothing but integral 1 to 2 1 upon x dx. Similarly, when k is equal to 3, the expression on the inside becomes summation j going from 1 to 2 integral j to j plus 1, 1 upon x dx, which expands to integral 1 to 2, 1 upon x dx plus integral 2 to 3, 1 upon x dx. Similarly, when k is equal to 4, the expression on the inside becomes summation j going from 1 to 3 integral j to j plus 1, 1 upon x dx, which expands to integral 1 to 2, 1 upon x dx plus integral 2 to 3 dx upon x plus integral 3 to 4 dx upon x. And finally, moving along in this fashion, when k is equal to n, the expression on the inside becomes summation j going from 1 to n minus 1 integral j to j plus 1, 1 upon x dx, which expands to integral 1 to 2, 1 upon x dx plus integral 2 to 3, 1 upon x dx plus integral 3 to 4, 1 upon x dx plus and so on. And the final term in this line is integral n minus 1 to n, 1 upon x dx. Now, the reason we went through this whole exercise is so that instead of adding up this entire summation horizontally, we can now add it up vertically, and we will see what advantage this gets us. The left-hand side, of course, is ln of n factorial, and the right-hand side, adding like terms to begin with integral 1 to 2, 1 upon x dx. There are n minus 1 such terms, k going from 2 to n. So this becomes n minus 1 times integral 1 to 2, 1 upon x dx. The next term is n minus 2 terms of integral 2 to 3 dx upon x, followed by n minus 3 terms of integral 3 to 4, 1 upon x dx, plus and so on. And finally, we have integral n minus 1 to n, 1 upon x dx. The right-hand side can be expressed as integral j to j plus 1, n minus j upon x dx, where j is summed from 1 to n minus 1. Now, in every one of these integrals, x goes from j to j plus 1. In this interval, the integral value of x is nothing but j. Therefore, ln of n factorial can be written as summation j going from 1 to n minus 1 integral j to j plus 1 n minus the integral part of x upon x dx. This can be expanded as integral 1 to 2 plus integral 2 to 3 plus integral 3 to 4 plus and so on, integral n minus 1 to n, and the integrand is n minus integral part of x upon x dx. Note that the sum of all of these integrals is integral 1 to n, and the integrand is n minus integral part of x upon x dx. Now recall that the integral part of a number x plus its fractional part is nothing but x itself. Therefore, the integral part of x is equal to x minus the fractional part of x. Substituting this in the integral, we get integral 1 to n, n minus, in brackets, x minus the fractional part of x upon x dx. And this is equal to integral 1 to n, n minus x plus the fractional part of x upon x dx. Breaking up the integral on the right hand side, we get ln of n factorial is equal to n times integral 1 to n, 1 upon x dx, minus integral 1 to n dx, plus integral 1 to n, the fractional part of x, divided by x dx. Now the integrand in the last term in the numerator, let's subtract and add half. We are basically trying to work our way to the final form of the integral that was given to us at the start. So the right hand side becomes n times ln x between the limits 1 to n minus x between the limits 1 to n plus integral 1 to n, the fractional part of x minus half upon x dx, plus half of integral 1 to x dx between the limits 1 to n. This is equal to n times in brackets ln n minus ln 1 minus in brackets n minus 1 plus integral 1 to n, fractional part of x minus half upon x dx, plus half of ln x between the limits 1 and n. This is equal to n times ln n minus n plus 1 plus integral 1 to n, the fractional part of x minus half upon x dx, plus half times in brackets ln n minus ln 1. Combining the two ln n terms, we get on the right hand side in brackets n plus half multiplied by ln n minus n plus 1 plus integral 1 to n, fractional part of x minus half upon x dx. ln 1, of course, is equal to 0. Therefore, 1 plus integral 1 to n, the fractional part of x, minus half upon x dx is equal to ln of n factorial minus n plus half times ln n plus n. Now the n at the end on the right hand side can be expressed as ln of e raised to the power n, which can also be written as minus of ln of e raised to the power minus n. And we'll see in a minute why we have arranged things this way. The right hand side becomes ln of n factorial minus, using properties of logarithms, ln of n raised to the power n plus half minus ln of e raised to the power minus n, which, using properties of logarithms again, is equal to ln of n factorial divided by n raised to the power n plus half times e raised to the power minus n. Now at this stage, let's recall an important result called Stirling's asymptotic formula, which states that the value of n factorial can be approximated by root 2 pi times n raised to the power n plus half times e raised to the power minus n. It is also known that the error from this approximation tends to 0 as n tends to infinity. In other words, the limit n tending to infinity, n factorial divided by n raised to the power n plus half times e raised to the power minus n is equal to root 2 pi. Now from the previous line, integral 1 to n, fractional part of x minus half upon x dx is equal to minus 1 plus ln of n factorial upon n raised to the power n plus half times e raised to the power minus n. As n tends to infinity on both sides, using Stirling's asymptotic formula, the right hand side becomes minus 1 plus ln of root 2 pi. And as n tends to infinity, the left-hand side becomes the integral 1 to infinity, the fractional part of x minus half upon x dx. The right-hand side can be calculated, comes to minus 0.08106, which is a slightly negative number, just like what we had anticipated at the start. And this is the required answer. I hope you had fun, and I will see you back at MathMuni for the next story, where mathematics comes to our rescue and saves the day. Meanwhile, check out mathmuni.com for hundreds of mathematical problems across a range of topics. We are rapidly expanding our collection and would love to hear your feedback. Please drop your suggestions in the comments below. Bye for now.